Hello guys, this is Rajesh. My roll number is 295182156. Branch Aeronautical Engineering and subject is Techniques in Wind Tunnel. So the topic name is losses in supersonic tunnel. A supersonic wind tunnel is a wind tunnel that produces supersonic speed 1.2 less than Mach number less than 5. Means the Mach number between 1.2 to 5. And this region is called supersonic speeds. The Mach number and flow are determined by the nozzle geometry. The Reynolds number is varied by changing the density level, pressure in the settling chamber. Therefore, a high pressure ratio is required for supersonic regime at Mach number 4. This ratio is of the order of 10. Apart from the consideration of moisture or even gas liquefaction can occur if the static temperature becomes cold enough. This means that a supersonic wind tunnel usually needs a drying or a preheating facilities. A supersonic wind tunnel has a large power demand, so most are designed for the intermittent instead of continuous operation. And engineers check an aircraft model before a test run in the supersonic wind tunnel at Lewis Flight Propulsion Laboratory. And this is the wind tunnel of a supersonic tunnel. And scale photography is often used to capture images of gas flow and shock wave in supersonic wind tunnel. Here, Mach 4 flow, Mach number 4 flow over a pitot probe is observed by scaling optics in the Penn State supersonic wind tunnel. The flow direction is left to right. And restriction for supersonic tunnel operation. Minimum required pressure ratio. Optimistic estimate pressure ratio is greater than or equal less than or equal to the total pressure ratio over normal shock at M is test section. PT by PAMB less than or equal to PT1 by PT2 of Mach number 1 equal to Mach number M1 equal to MM. And temperature effect consideration. Temperature in the test section Tm by Tt equal to 1 plus gamma minus 1 by 2 of mm square power minus 1 with Tt equal to 330 kilo and Tm equal to 770 k at m is equal to m Mach number equal to 4. The velocity range is limited by reservoir temperature and power requirement. The power required to run a supersonic wind tunnel is enormous, of the order of 50 MV per square meter of test section cross-sectional area. For this reason, most wind tunnels operates intermittently using energy stored in high-pressure tanks. These wind tunnels are also called intermittent supersonic blowdown wind tunnels, of which a schematic previous is given below. Another way of achieving the huge power output is with the use of vacuum storage tanks. These tunnels are called in-draft supersonic wind tunnels and are seldom used because they are restricted to low Reynolds numbers. Some large countries have built major supersonic tunnels that run continuously. One is shown in the photo. Other problems operating a supersonic wind tunnel include and starting at unstart of the test section related to maintaining at least minimum pressure ratio, adequate supply of dry air, wall interference effects due to shock wave reflection and sometimes back blockage, high quality instruments capable of rapid measurement due to short run times in intermediate tunnels, and tunnels such as Ludwig tube have shortest times usually less than 1 second, relatively high Reynolds number and low power requirement. This is the tunnel of high pressure tank. Here's some schematic diagram, and these are the parts of wind tunnel. Nozzle. Losses in nozzle. In nozzle, three pressure losses comprise the total pressure loss through the nozzle, entrance loss, through, through nozzle loss, and exit loss, entrance loss, through nozzle loss, and exit loss. Fluid mechanics provides methods for calculating pressure losses through pipes. And condition for supersonic nozzle. As it exits the nozzle, the gas is typically moving and therefore at a lower pressure. In order to create supersonic flow, the first important condition is a high enough pressure ratio between the combustion chamber and the throat of the nozzle to guarantee that the flow is sonic at the throat. The high temperature, high pressure gas the expanded through the supersonic nozzle, in which it reaches a very high velocity. The SRM is one of the most common type of rocket propulsion system and has a wide variety of application. An SRM is conceptually a very simple device with a very few moving parts. Thank you.